As we go further, we like to talk about 3D printing for manufacturing today. So there's 6 basic talking points when it comes to manufacturing and 3D printing. The first being changes in the economics of production. So what that basically refers to is the repeatability factor of 3D printing. So being able to print the exact same piece out several times over without any additional cost associated with first initially starting. Usually there's some high cost associated with manufacturing of a certain device or part because you to get that dollar amount down, you have to print in a high volume. With 3D printing, that's not necessarily the case. The second point is design freedom. So due to the fact that this is additive, we're building these parts and pieces out of the combination of different materials stacking up on one another. You have more freedom in the sense that you're not limited to the manufacturing that you're typically used to. So CNCing, water cutting, lathes, you're always taking away from a larger piece of material, whereas 3D printing is the opposite of that. That, in tandem with soluble support, allows you to pretty much print any geometry that you would like to. That being said, that kind of goes into number 3, which is increased part functionality. So essentially printing for function as opposed to those limitations in manufacturing that I just mentioned. Number 4 is product personalization. So as the technology has developed and come further along with materials and applications, you now have newer abilities to get everything from photorealistic prints with full color spectrums to more versatile and functionality in parts, even being able to print out full assemblies with no additional assembly required. Number 5, the environmental sustainability factor. That refers to the just-in-time manufacturing of 3D printing. So printing out exactly what you want, when you want it, without having to waste any materials or time that isn't needed. And then last but not least, number 6, the new supply chains and retail models refers to basically localizing your manufacturing environment. By having a 3D printer in-house, you don't need to outsource as much as you used to or at all. And you could also get certain replacement jigs and fixtures, parts, end-use parts, what have you, to your customers much faster. But for the sake of this presentation, we're really going to focus on numbers 2 and 3 only. So what you're going to see on your screen now, once it loads, is we're going to go right into Stratasys Technologies. So the first one is FDM, or Fused Deposition Modeling. So hopefully this video is coming out clear on the broadcast on your end. And essentially what you're seeing is the FDM process wrapped up in this video. So the way this works is it has 2 different spools of what's called a thermoplastic filament. So one is model and one is support. So what it's doing essentially is melting this plastic down, or getting it hot enough to its melting point that it can then be pushed out by the heads to make these structures layer by layer. It will take turns between extruding model material, which is the material that your actual part will be consisting of, and then support material, which is what helps your model be built with different geometries that we mentioned earlier, which can then either be broken off of your model part or be washed away in a soluble support bath. As we move further, we have here a chart of all of the current fused deposition modeling materials that are in our catalog. The first category being general, so we have our ABSs, Plus and M30 are the typical run-of-the-mill ABS configurations. ABS M30i, however, is biocompatible with gamma rays. ABS ESD7 is a static dissipative material, so it's really good when working with certain microchips and computer processes. It's also repellent to certain molecules and dust particles, so it's good for delivery systems such as inhalers. ASA is essentially the new and improved version of ABS, which we'll be getting into a little bit further into the presentation. Then as we go into the next category, engineering, we have polycarbonate blends. So polycarbonate ABS, and then polycarbonate iso, which is the biocompatible version of our PC materials. And then nylon 12, which is another material that we'll be getting into a little bit later. The high performance category has our ULTEM series of materials, 9085 as well as 1010, which we will also be getting into. And then finally we have our specialty products, so ST130, ST standing for sacrificial tooling, to be used to invert model and support, meaning you can print in full support to then do carbon wrap-ups and things like that to then wash away that model material to then have nice carbon wrap-up tubes and things like that, usually used with high-end automotive applications. SR35 is coming soon. That is a new type of soluble support powder. It's basically the new and improved version of SR30, the typical soluble support that we use here. Nylon 6 is a new material that was just released today, actually, which I'll be talking about a little bit later when we get into Nylon 12. And then ESD PEC is similar to ABS ESD7, whereas it is electrostatic dissipative, but PEC specifically is used for outer space, so things like the International Space Station, or the ISS for short, as well as satellites and things like that. But we're going to start by getting into ASA. So a couple things about this material. Right off the bat, it's UV stable, which isn't seen with most other materials in our catalog. It also has the best aesthetics of all FDM thermoplastics, meaning that just by the chemical composition of the material, it comes out looking as a high resolution. So the layer lines that you see on all types of 3D printing parts aren't as prevalent on ASA as opposed to some of the other thermoplastics. It also has superior mechanical capabilities to ABS, so things like tensile strength, tensile elongation of break, things like that. It's slightly higher in those categories. And you can see some pictures in the middle pertaining to outdoor use because of UV stability. A couple different colors there, up to 10. And also the bridging capability that it has, meaning that it, again, due to the chemical composition of the material, you can actually extrude in a more sparsed out function. So you don't have to have parts as solid as you would have to traditionally make them in. So if you have an application that requires less sparsing needed, this is a really good tool to use. And then some applications, just to list some, are functional prototyping, again, lighter, more cost-effective concept models due to that bridging capability, custom end-use parts for outdoor because of the UV stability, and then investment casting, which we'll be getting into right now. So here's our first case study, RLM investment castings. As you can imagine, they do investment castings. And now why ASA? The benefits from using ASA are more design freedom, lower ash content, and enormous time and cost savings. Lower ash content meaning because you can sparse out these parts and still retain the outer geometry as opposed to ABS or any thermoplastic, you can get the same results from something like investment casting without having as much wasted product or burnt out plastics collecting within that deposit. So it makes for a cleaner, more efficient investment casting process. And traditionally speaking, that is comparable to $5,000 to $20,000 machine patterns that are typical in this industry. And then we have a quote here from Rick Meacham, VP of Sales for RLM. They were essentially able to get perfectly matching gear sets and started going right into the production in about 7 days, as opposed to weeks of having outdoor companies machine these parts. Moving on from ASA, we then go into Nylon 12 in our engineering catalog. So a couple things about Nylon 12 right here. We have strong chemical resistance. We have 30% elongation of break, the most of any FDM thermoplastic, and also high fatigue resistance. Now because of that elongation of break and the strength that is also backing up, this type of material is very good for snap fits, as well as friction fit inserts, things like functional drill guides, prototyping, end-use parts for ducts and things such as that are very good in terms of how to use Nylon 12 effectively. And our case study here with Nylon 12 is the Red Dot Corporation. Why did they use Nylon 12? Because their final parts were nylon, and instead of having a nylon-like material such as Nylon 12 to prototype in, they had to machine these parts. So there was a lot of cost that didn't need to be accrued because of what they were forced to use traditionally. So obviously prototyping in a nylon material for your end-use nylon parts are very significant in terms of the benefit towards you. Also, the semi-crystalline nature of Nylon 12 allows it to withstand a lot of the testing that you see when trying to figure out how a prototype should look and how the end result should look. In addition to that, you also have less wasted metal tooling and lower tool cost from metal modifications. Traditionally speaking, they would spend about several $100,000 on these types of metal prototypes, so you can see why they went this way. And a quote from Gary Hansen, the VP and CTO of Red Dot, they can now make nylon prototypes with nearly the exact same properties as production parts, which is obviously very good for them. And I mentioned Nylon 6 earlier. This is a new material. You can look this up today on Stratasys website or catdimensions.com. Essentially, Nylon 6 falls as a combination almost between ASA and Nylon 12, the two materials we already looked at. So Nylon 6 is UV stable, has a high chem resistance as well as in similarity to Nylon 12. It also has about a 19% elongation of break, And the second runner-up from that would be polycarbonate with 9%, so you can see how big of a factor that is for those percentage points. And then it's also stronger than ASL and nylon 12. So we're expecting to see a lot of use at nylon 6, mainly because it's a more traditional nylon used in production. Moving from that, we then get into our ULTEM materials, 9085 and 1010. So the first one we start with is 9085. A couple things about 9085. It has a flame, smoke, and toxicity rating, FST for short, which basically means if this material is in an environment that's so hot, the material starts to melt and give off a smoke. That smoke is not toxic to humans at all, which makes it great for aerospace when you don't have access to open air. Also has a very high strength-to-weight ratio, going again to the aerospace applications. Airbus, for instance, has about 1,000 3D printed pieces on board in their new systems. And because of this aerospace application, there's ULTEM 9085, specifically called ULTEM 9085 Aerospace for this nature. There's also a certification grade, which can be sterilized for different uses. You see a lot of end-of-arm tooling and metal forming as well as thermoforming with this type of application. And once again, going into aerospace, because of how strong, durable it is and the strength-to-weight ratio that you're getting from this material, it could really hold up with some of the most stringent aerospace industry requirements. And one example we have for you here is Piper Aircraft based in Florida. So they make single and double engines on personal aircrafts. So why do they use ULTEM 9085? A couple different reasons. One being that they were able to get 10,000 PSI resistance or more based off of this material. They also didn't need an operator in attendance. We essentially have lights out manufacturing, so you could start a 60-hour build on a Friday afternoon and come back Monday morning and it'll be completed with no issues and not having to babysit your parts. And also, you have much less wasted material going back to traditional versus additive manufacturing methods. And FDM is normally faster than CNCing anyway. And traditionally speaking, they were machining these parts out of aluminum, which has a high cost and obviously lots of waste associated with that. We have Jake and Allenbaugh, manufacturing engineer, Piper Aircraft, that said he was able to program an FDM part in 10 minutes, while a typical CNC program takes about 4 hours to write. So in addition to the cost savings of the materials themselves, there was also a huge time-saving portion of this application here, which allowed Jacob to then devote his time to more important and more pressing matters. As we move on, we go into ULTEM 1010. So this material has the highest FDM temperature resistance and fire resistance out of all the other thermoplastics. It also has the best chemical resistance, the highest tensile strength, and the strongest FDM material overall, with the lowest coefficient of thermal expansion. And this material also has FST, or flame, smoke, and toxicity rating. So this typically is used for things like high pressure valving. It can be sterilized in an autoclave, so there's a lot of autoclaving that can be used for medical applications. And then a lot of layup tooling for larger pieces like the parts of airplanes that we can see with companies such as Boeing because of how strong and durable this material is. And similar to 9085, you see ULTEM 1010 being used for a lot of metal forming and thermoforming, layup tooling like I just mentioned, food production because of its certified grade, the autoclaving that I mentioned, and a lot of aerospace and automotive components. And a newer application that's being further looked into by Stratasys and is being developed further by their team is compression molding. So being able to mold a charge of various materials by having molds made out of this material is unprecedented. Usually you cannot do this in any plastics. So we're seeing a lot of groundbreaking movement happening in that type of application. And our case study with ULTEM 1010 is UTC Aerospace Systems. Just as a little bit of background on these guys, what they normally do is they make a lot of different parts for onboard use for various aircrafts, both military and civilian. But more importantly, the machines that they use are where ULTEM 1010 came into play. So there was a lot of different valving features and portions of their machines that would break down over time. And instead of having that designed again by an engineer and machined in metal, they were able to replicate this with ULTEM 1010 plastic. And the benefits were 8 months of life out of those parts, the high repeatability of 3D printing, so if it broke, you're just able to print out another one, again, significantly cheaper and faster than getting it milled or machined. Tooling jigs and fixtures for the rest of their facility once they realized how versatile the technology is. And then, again, this is high pressure valving we're talking about, so several hundred PSI constantly going through at any given rate. And we have another quote here by Larry Crano, an automation specialist at UTC Aerospace. The rugged factory environment often puts high demands on 3D printing materials, and based on our experience, ULTEM 1010 is fully capable of meeting that challenge. Now, the second technology we go into is PolyJet. So this is fairly different than what you have come to know with FDM. This is not a thermoplastic, but a photopolymer. So the process that you're seeing here, it's somewhat similar in a way where you have layers of this material building upon one another. However, the delivery method is much different. Instead of a spool of filament, you have material jetting happening. So essentially there's canisters of this liquid photopolymer that are then sprayed out into a mist or dot matrix of various materials similar to an inkjet printer, which then has a rolling mechanism coming over each layer to smooth it out and flatten each layer to resist bubble buildup in the parts to make sure they are as solid and consistent as possible. And there's also two lights that follow the movement of the head at any given time. So instead of having a partially cured part that you would see with an SLA system, for instance, the parts that come off a PolyJet system are completely cured right off the printer. So all you have to do after that is remove support. Now we have soluble support for PolyJet, so you can now just throw it in a tank and walk away. And then do any post-processing you see fit, anything like sanding, painting, although painting might not really be necessary with the newer technologies because of the high color spectrum that we boast. So here we have our PolyJet catalog. There's a lot that's going on the page right now, but to break it down simplistically, we have our general rigids on the left, which have basically all of our colors and our non-flexible materials. So our Vero family, our blues, grays, blacks, and whites, yellow, cyan, magenta, as well as clear, our simulated polypropylenes as well. In the general flexible category, we have our Tango family, which are our different flexibles with different tear rates and elasticity ratings. We have our engineering catalog, which has digital ABS as well as high temperature materials, and we'll be getting to digital ABS a little bit later. And then finally, we have our specialty dental category, so things that would pertain to making, say, Invisalign braces is where you see a lot of the medical and dental applications coming into play. But to get started, we're going to go into our general rigid catalog with our Vero family. So this is considered a rigid opaque. What that basically means, as the name implies, is these are not flexible materials and they're also not translucent. So you're literally getting a rigid opaque structure. And they're good for a couple different applications, but one that we'll be getting further into is silicone molding, specifically with Vero Blue. So why do they use PolyJet in particular? Well, in regards to Vero Blue, it actually reacts less to silicone, meaning you have more crisp and concise molds coming off of this PolyJet technology as opposed to any other kind. And the layer lines are fairly non-existent or not as present and noticeable as you can see with FDM or any other type of 3D printing process. Furthermore, because this is 3D printing, it generally costed approximately 80% less than traditionally CNCing these parts. As a bit of background, ADLER Trio is a musical group, so they were making their own flutes and other types of musical instruments, usually out of plastics or woods, and because of that, they didn't have a lot of freedom of design and complexity with their parts. And a lot of the time, they would have a rattling within the mechanisms, so they would have to actually put silencers on these parts to make sure that there wasn't any additional spoiling sound that would affect their music. Now, also in addition to that, being used for 3D printing, you have more complexity available without the lead time or cost associated with having machine parts. And a quote here from Dror Adler, the musical director of ADLER Trio: "With PolyJet patterns and RTV molding, we were able to produce amplifier housings that make it easier to play the harmonica, sound better, and look much more professional." And just as a little background, RTV molding is room temperature vulcanization. Moving out from that, we are going to go further into digital ABS. Now, a little bit on digital ABS. This is considered digital material. Now, digital material is a term that you see consistently in the realm of PolyJet. We have a graphic here to kind of explain what that means. Essentially, it's combining two or more materials together. And the higher up in the systems you go, the more materials you have at your disposal. Currently up to 6 different material combinations at any given time with the J750. And what that basically is doing is you have your primary material, your secondary or third or fourth type of material. They can be rigid or flexible depending on what you want to make and what type of durometer you want to get out of these parts. and they're essentially mixed together into a dot matrix, which is then considered digital material, which is a composition of primary and secondary materials that you inputted into your system. And this is so prevalent that if you cut a part in half made on a PolyJet system and put it under a microscope, you'd actually be able to see the individual droplets, but not to the naked eye because we're looking at about 600 drops per cubic inch. Now, there's a video here on your screen, and this is a start to finish by the Berker company on making a light fixture out of various injection molding processes using digital ABS. So we're starting here with the CAD process and then going right into the printing. Now, a couple things I want to point out as this video progresses is the fact that you're going to see a couple different materials being shot into these molds, which is important to note because with the differences in materials, you're going to have different cycle times, you're going to have different shot cycles out of this. So the number of shots that you get out of each specific mold is extremely dependent on what you're shooting in specifically, and more importantly, injection pressure. Injection temperature isn't necessarily an issue because these photopolymer materials are thermoset, meaning that they will actually catch on fire before they melt and lose their geometries. But going back to the visuals that we have here, they already printed out their pieces, they've reamed holes for injector pins, and are now installing them onto their mud bases. You'll be seeing materials such as polycarbonate, ASA, and TP throughout, but we have customers all throughout our territories and worldwide with Stratasys that are using these materials in a much broader approach and way more materials than just the three that I've mentioned. There's one company called Seufer out in Germany that shoots TPE into their materials and a different type of simulated polypropylene, and they're able to get several hundred shots out of their molds as opposed to 50 here and there. And going back to the video, we have the trimming and cutting of the gates and other types of hanging bits off of these molds. And at the end of the video, you're going to see them completely assembling this light fixture start to finish with every single part that you just saw them injection mold. So it shows a very holistic approach to what 3D printing can do for your process. Now a bit of summarization on what we've been talking about now. This slide kind of goes into PolyJet advantages as well as FDM advantages. So there's a couple on either side. In regards to FDM, you have tough aesthetic colors, strong durable ABS, medical and food contact, versatility, specifically in regards to things such as the ULTEM series of materials as well as the NYLON series of materials, economic sparse fill in regards to ASA, and then high performance end use parts. Whereas the PolyJet, you're looking at color range, molding and tooling, smooth surface finishes, multi-material realism. You also have polypropylene-like materials. Going to the Tango family that I briefly mentioned earlier, we have different choices of flexibilities, as well as ABS functionality, clear transparency, thin walls and cavities, and then finally medical and dental, going back to the Invisalign braces application that I mentioned earlier. But to summarize that, essentially, if you're looking for strength and durability with 3D printed parts, FDM is really where you want to go. The technologies boast much stronger materials, again going back to the ULTEM 9085 and ULTEM 1010, that can resist up to 10, 15, even more than that, 1,000 psi resistance. That isn't to say that PolyJet can't be used for strong and durable parts. Digital ABS, as we just saw in the Berker video, is kind of a testament to that. But typically speaking, PolyJet is considered to be more so used for shiny, tiny, and pretty applications. So complex geometries and prototypes and models that require a high resolution, because there is a higher resolution with PolyJet due to the technology. Although it is important to note that the accuracies of the technologies are fairly similar. With PolyJet, you have anywhere from 32 to 16 microns of accuracy, although with the J750, you have up to 14 microns. And then with FDM, you go anywhere from 13 thousandths of an inch to down to 5 thousandths of an inch. Again, going back to what technology or system that you're using, as well as what material that you're printing out with. Now, that being said, that pretty much wraps up what we had presented to you here today. We like to end this by asking if you have any questions. And if you do, we like to cut about 5 or 10 minutes into our presentation now to allow you to type those questions into the question box, and I will answer them audibly on this call. If you don't want to answer, or if you don't want to have any questions presented now, you could always contact me personally. My email is listed on the screen right now. My whole job is to answer these types of questions that you may or may not have. And also we have a PDF version of these slides that we could give to you if you'd like. So I'm just going to stay on the line for a few more minutes and wait to see if any questions come in. If not, I'll sign out. And again, thank you very much for listening today.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.